All right. Well, thank you so much. Can you hear me well? Okay, awesome. And also, can you confirm I have 50 minutes plus 10 questions? Okay, awesome. Thanks. All right. Well, I wanted to say good morning. It's 6:30 here in California. Greet from Merced. It's my pleasure to give this talk, and thank you so much for the organizers to invite me. And I would like to be there. Unfortunately, I can't. I have a small child who needs me here all the time, and so for the time being, I'm trying to do my best and contribute to the community via these virtual events. I hope you enjoyed the workshop, and let's get started. So yeah, so the title of this framework is hIPPYlib-MUQ. As the name suggests, it's actually an interface between two frameworks, computational tools. One is hIPPYlib, and I will explain each of them in detail, but just a quick reference. H is really just there to complete the word, and the rest is inverse problems Python-based library, and MUQ is the MIT UQ tool developed by Matt and others, and I will get back to it in a few slides. So I would like to mention that this is joint work with several people. My former postdoc, Kite Kim, who used to be at UC Merced, and now he is at Lam Research Corporation, with my collaborator, Umberto Villa, who is at UT Austin, with Matt Parno, who used to be at MIT and then at Dartmouth, and now he is at Solia Energy. With Youssef Marzouk at MIT, and with my former postdoc advisor, Omar Gattas from UT Austin. And since this is a computational challenges and emerging tools workshop, I thought that I should focus on perhaps challenges that we are facing when solving inverse problems governed by PDEs and, well, emerging tools, right? So hopefully this is useful for you guys. Okay, so before I start, I would like to acknowledge a couple of sources. So all this project actually started a couple of years ago, and we submitted a grant to the US National Science Foundation, and we received funding, and the PIs are Omar, Youssef, Matt, myself, and Umberto. And really the proposal was to push this inverse problems library a bit more to be useful for the community, and also to interface it with MUQ, which brings in lots of state-of-the-art UQ tools. I would also like to acknowledge NSF for my career award. I have been funded through this award in the last couple of years. And I would also like to acknowledge lots of computational resources, including the local Merced cluster here in campus. All the results that we have obtained for this latest paper summarizing hIPPYlib-MUQ have been obtained on this small cluster. And also I would like to acknowledge the Advanced Cyber Infrastructure Coordination Ecosystem, this new access program that gave us support to create all kind of tutorials and all that stuff. And also, before I start, I like to apologize in advance for not putting too many references on my slides. It's really just impossible. I'm in general in favor of having all kind of good references and things to share, but it's just too much. So instead, I would refer to these two papers that have been fairly recently published in the Transactions of Mathematical Software. So hIPPYlib is described in this paper, which was published in 2021. You can find it also on arXiv. There is also a nice Docker container or image containing the pre-installed software in examples. You can find this link in the paper, or you can just Google it and you can download and try out all the examples and tutorials that we have described in this paper. And also this particular workshop, well, this particular presentation is focusing on hIPPYlib-MUQ. And this has been summarized, all this work has been summarized in this very recent paper, which is published in, or to appear, or just accepted, I suppose that's the stamp on it right now, in the Transactions on Mathematical Software. And also for this, we also have a Docker image, and you can play around with the software and with the examples that are in this paper. Okay, so let's see, how do we begin? Motivation, I might preach to the choir here, but I would like to give you a couple of motivational points or slides at the beginning. So as you know, in the last couple of years, we have seen tremendous growth in observation and experimental data that are being collected, stored, processed, and analyzed. And pretty much everyone is trying to ask a question, how do we extract knowledge and insight from all this data to make better predictions via various ways? As you know, when the data corresponds to observations of natural or engineered systems, and these systems can be represented by models, this knowledge from data problem is fundamentally a mathematical inverse problem. And the way we formulate these problems are as follows. Given some possibly noisy data and a possibly uncertain model, our goal is to infer parameters that characterize the model. So a couple of examples of inverse problems governed by PDEs, or even differential algebraic equations. I would start with one of my favorite ones because I've spent a lot of time in researching, doing research in this area. Ice-sheet basal sliding from satellite observations of surface flow. And on the right, I'm showing these two pictures. For instance, the top one shows satellite observations of ice flow velocity fields. That is real data in some measurements. And at the bottom of the figure, for instance, I show the reconstruction, or yes, the reconstruction of the so-called basal sliding coefficient field in an ice-sheet model that is governed by a nonlinear Stokes equation. Other examples, for instance, one may wish to infer parameters, for instance, the inertia and states for power grid, for instance, from voltage measurements. This can be modeled as a DAE, or differential algebraic system, or one could formulate an inverse problem to infer Earth structure from reflected seismic waves, or 3D bone structure from X-ray CT measurements, and so on and so forth. What these problems have in common usually are governed by differential equation based or differential equations. And these models are often subject to considerable uncertainty stemming from unknown or uncertain input model parameters, as well as from noisy and limited observations. So the big goal here is to infer these unknown model parameters from observations of model output through corresponding or underlying PDE models, or PDE-based or differential equations-based models, and to quantify the uncertainties in the solution of such inverse problems. And I will zoom in to, again, the first inverse problem example, the ice-sheet basal sliding inversion from satellite observations. Why is this important or interesting or challenging? Well, this, and most likely all of these inverse problems, basically. Number one is these problems are governed by a complex forward model. The dimension of these problems is really high. The dimension stems from discretization. And there are lots of uncertainties due to approximations, right? Simplifying assumptions, several sources of uncertainties, more or less important in the model, and so on and so forth. And so in order to do prediction, we need models that we can rely on. And good models should give you reliable prediction. So for instance, here I advocate for the need for predictive models with quantified uncertainties to accurately anticipate future sea level rise. And why is this important? If you check the latest IPCC reports, and you might want to also play around with this really nice sea level projection tool offered by NASA, you will see that the future in terms of sea level rise, it doesn't look very well, not very optimistic. Basically, several port cities are predicted to be at risk from coastal, and it's actually happening already, right, from coastal flooding in the future. It turns out that the studies show that ice flowing from ice sheets to ocean is primary contributor to sea level rise. So the glaciology or ice sheet community is trying to come up with better models to make more reliable predictions to, of course, down the road to help with decision making. So what are the challenges, mathematical challenges when solving these problems? For instance, this ice sheet problem, I keep coming back to this because it's one of the most challenging inverse problems I have been working on in the last couple of years. Several mathematical and computational challenges place barriers on improving predictability of, for instance, ice sheet flow models. I will give you a couple of examples. The geometry is quite complex with very high aspect ratios. There's a highly nonlinear and anisotropic rheology, extremely ill-conditioned and large-scale linear and nonlinear algebraic systems that arise upon discretization. There are lots of uncertainties in the model. For instance, the Bayesian sliding parameter that lives, it's a parameter that lives at the base of the geometry in form of a coefficient field in a Robin boundary condition. Basal topography is uncertain, geothermal heat flux, rheology, and so on and so forth. There is a lot of modeling error that goes into the system. I will not focus on this last aspect in this talk, but I invite you to check out some of the references in our papers with respect to this work. I would like to mention that these pictures and these figures on the right, again, I'm showing the top surface velocity field. And I'm also showing a figure that shows some sort of decay. This is actually the spectrum of a second derivative of the cost function in our inverse problem. This basically shows that there is a lot of structure that one can exploit and push these methods towards a more tractable way to solve these problems. Okay, so how can we address some of these challenges? We infer unknown uncertain model parameters from available data. So this is goal number one. Again, the challenge with this is that it's a high dimensional problem. We need to solve the forward problem many times. But we can formulate this as under the hood of a statistical inverse problem governed by PDEs, and then apply tools that are available, methods, algorithms. We need to apply, adapt, design fast mesh-independent structure exploiting inner product and additional uncertainty-aware methods so that we arrive at a scalable, robust, and efficient algorithm can be used to solve these problems. And another aspect another way to address some of the challenges in terms of improving the quality of the data, this is something I will not discuss today, but again, I invite you to check out our references, is to collect data in an optimal way in order to minimize the uncertainty in the inferred parameters or in some predicted quantity of interest via optimal experimental design. I put here a nice reference by Omar and Margatas and Karen Wilcox that appeared fairly recently in Acta Numerica, which summarizes these techniques quite nicely. Something that I want to mention up front is that this talk is not about developing methods. It's hIPPYlib-MUQ brings together state-of-the-art methods that are available in the community and implement some of them. And I will show you how this is done and also how some of these methods perform. Okay, sort of a big picture thing to summarize all the components that come in place when we solve Bayesian inverse problems. If in case you are not familiar, Bayesian inverse problems or Bayesian inference rely on Bayes' theorem, which gives you a posterior distribution, which can be written as such. It's proportional to something like the likelihood and the prior. The prior can be modeled in various ways. Here I'm showing with red a prior placed on this input or on certain parameters, and could be, typically we model it as a Gaussian, so mean and covariance. We'll talk about that later. So starting with that and using the model and the data, we formulate a likelihood. Basically that will look at the difference between the prediction and the data, and using that form, we can compute, or we can characterize a posterior via various ways. Here we are going to focus on sampling methods, MCMC sampling methods, to explore this posterior, and that will give us at the end the uncertainty or certainty on the inference in our inversion. Once you have that, then you can do more. You can use that uncertainty to predict for prediction, and we are taking account all that uncertainty that you computed. You can also do optimal design, optimal experimental design or control, and so on and so forth. And all this will be aware of all the uncertainties in the model and inference in the model. These are, we like to call them, or actually the whole community nowadays it calls this these outer loop problems. So this hIPPYlib-MUQ framework comes to help solving all these problems. And one challenge that I did not mention is that to implement methods to solve these problems, one really needs lots of background in various fields. And so hIPPYlib-MUQ is coming in kind of as a help or a tool to speed up perhaps the time to implement these methods and solve problems a bit more in a more practical way, if you wish. All right, so our motivation to develop this software framework, and I will just go over some algorithmic and computational challenges. As I already alluded to, characterizing the posterior requires repeated evaluations of the forward models, possibly large-scale PDE models. The posterior distribution often has a complex structure stemming from nonlinear parameter to observer mapping and heterogeneous sources of data. The parameters are often fields, which when discretized lead to very high dimensional posteriors. And so these difficulties render complex large-scale PDE-constrained Bayesian inverse problems pretty much intractable via standard MCMC methods. Some of the implementation challenges that we faced, methods that facilitate the solution of Bayesian inverse problems governed by these models, as I mentioned, require a diverse and advanced mathematical and computational background. And to be efficient, as I will show you in this presentation, these methods generally require some sort of something about the structure or curvature of the underlying mapping via first and second derivative information, which can be cumbersome to derive. So again, the goal here is to offer a software framework aimed at overcoming these challenges and providing capabilities for additional developments for Bayesian inverse problems. And really our motivation initially started from the need to help our students and our groups to jumpstart their research projects and to do all kind of algorithmic developments and prototyping. And later we realized the benefits of this tool or tools, and we decided to make them available to everyone. And for some reason, my outline is broken. Okay, so first part of this framework is hIPPYlib, which I mentioned, is an inverse problems Python library. We call it extensible software framework because the hope is that one can start with what we put together and extend it fairly easily to various needs with minimum amount of modifications. Although, truth be told, every time the problem changes, it's really takes a bit still to adapt and extend things. But it's a good starting point, and it really saves a lot of time. So if you have not checked it out, please do. In hIPPYlib, we focus on deterministic inverse problems, and we can also form or do sampling from the Laplace approximation of the posterior. Basically, we just do a Gaussian approximation around the so-called map point, which is the solution of the deterministic inverse problem. For the rest, a more full Bayesian inversion can be done only using MUQ. hIPPYlib contains the implementation of adjoint-based algorithms for PDE-based inverse problems. Currently it builds on Phoenix, which probably most of you know, or if you don't, this is a parallel finite element library. And we use Phoenix for the discretization of the PDEs, and we rely heavily on PETSI, also through Phoenix mostly, PETSI for scalable and efficient linear algebra operations and solvers. hIPPYlib is implemented in a mixture of C++ and Python. C++ just because there were some capabilities that we needed and were not available in Phoenix. And it has been released under a general public license option. I would like to emphasize that hIPPYlib can be useful not only for research purposes, but also it's a really good tool for learning and teaching. I use it in my inverse problems class, and some of my collaborators are also using hIPPYlib as a teaching tool. The latest version is 3.1, and it can be downloaded from GitHub. And again, I invite you to check out this Tom's paper for details. And here I cannot go into the mathematical derivations in detail for specific problems, but we do that in this paper in detail. Okay, some of the algorithms or software contributions that we have in hIPPYlib. It's really a modular approach to define complex inverse problems. Again, we try to keep in mind that the user should be as non-invasive as possible when it comes to modifications. And so we try to keep that in mind. We implemented adjoints and Hessian actions needed to solve the underlying deterministic inverse problem. We use inexact Newton CG to solve the optimization problem with line search, with an Arm-Hio type line search to guarantee global convergence of the optimizer. We have also implemented randomized SVD and randomized algorithms to compute low-rank factorizations of the misfit part of the Hessian of the inverse problem objective. And as I mentioned, we also construct and evaluate the Laplace approximation of the posterior. We also implemented sampling, so you can apply the square root of the inverse of the Hessian to random vectors and get sampling from this Laplace approximation. And we also estimate the pointwise variance of the prior distribution and the Laplace approximation of the posterior. So these are the things that hIPPYlib offers in case you are wondering what exactly it's implemented there. At least in the released the public version, there are a couple of new developments in the development version, but we'll not talk about that here. Okay, we have been using hIPPYlib for a while now for many applications. I hope this will give you an idea of if you work in some of these areas, if it's something that would be useful for you. For instance, in optoacoustic tomography, this is something that is done by Umberto and others. Acoustic scattering, just to give you more examples, seismic electromagnetic inversion, ice-ocean interaction, some more bio, cardiac tissue, inversion for material properties for that turbulent combustion. And I realize that I put mostly Austin here, so I should probably mention a few that you see Merced as well. Something from mechanics of nanoscale filaments. Recently, I got into model error and characterizing model error. I'm more and more interested to understand how to incorporate additional uncertainties into these inverse problem frameworks. I'm looking at the so-called Bayesian approximation error approach for inverse problems. I'm also interested to approximate the Hessian for various reasons, for preconditioning, the Newton system, for constructing better proposals for MCMC via this hierarchical off-diagonal low-rank approximation in the context of ice-sheet problems, and so on. So, as I mentioned, we use hIPPYlib also heavily as teaching tool, and there are so many workshops and summer schools and mini tutorials that we try to help with. I would just like to mention the last one at the SAM Conference of Mathematics of Data Science. We have a mini tutorial on inverse problems. And I would also like to mention the Jingolob summer school. And the reason for that is that there is a really nice, on this website, so a couple of pedagogical tutorials that one can check out. It's you can use hIPPYlib to run those. And as I mentioned, hIPPYlib is used also at as in inverse problems classes at various universities. Okay, so MUQ, I will not go too much into detail here because I am not involved actually in the developments of MUQ. I would like to mention the following reference, the MIT Uncertainty Quantification Library, which is it's a just very recent publication by Matt Palmer, Andrew Davis, and Linus Sillinger. You can download it from their website. Basically, MUQ provides an, I would not say easy to use, but if you know what you're doing, I guess it's easy to use framework for defining and solving uncertainty quantification problems with complex models. It's also implemented in a mix of C++ and Python. It allows sampling of non-Gaussian distributions, and this is actually why we were interested to interface with MUQ to bring in these additional UQ capabilities to hIPPYlib. So basically, hIPPYlib offers all the problem setup and derivatives and adjoints and Hessian applies, and then we use MUQ to build proposals and explore various Markov chain, Monte Carlo sampling techniques. MUQ also offers more than that, and you can use it as a separate tool, of course, or extend things. The nice thing is that you can, it's an open source software, so you can contribute, you can use it in however you need to use it for your application, but it allows you to approximate forward models, we have polynomial chaos expansion and Gaussian process regression. You can use MUQ to work with Gaussian processes and so on and so forth. Okay. So how does the integration look like? On the left, we have hIPPYlib, and it's all in orange. And then some libraries that we also rely on, like Phoenix and Petsy. And the hIPPYlib model basically consists of the PDE, and so the description of the forward problem. We have first and second order derivatives, and so adjoints. We define the likelihood. We have an observation operator built in. This will allow you to choose what kind of observations, if you want pointwise observations or observations everywhere or parts of the domain and so on and so forth. You can define the noise covariance. You can define the prior. Right now, the prior, we typically use some Laplacian based priors. Basically, we build Gaussian priors with a covariance given by Laplacian or by Laplacian, basically following Andy Stewart's African America paper to be consistent with infinite dimensional inverse problems. We offer also the ability to define various quantities of interest and the prediction and compute sensitivities. And as I mentioned, the algorithms consist of kind of optimization related algorithms, inexact Newton CG, randomized linear algebra, eigensolvers, trace diagonal estimators, and so on and so forth. On the right, we have MUQ and its modeling capabilities. You basically specify the model. You can use the gradient and Hessian computed in hIPPYlib to build proposals for sampling, and we don't really use, at least we did not explore the surrogates and prediction tools such as global sensitivity analysis and optimal experimental design, but these are there if you wish to explore. And then the interface physically connects, takes all the model information and derivatives, and takes all the sampling capabilities from MUQ and brings them together. Probably no need to go deeper than that. As I mentioned, all this is available on GitHub. Okay, so let's look at an example. This is one of the examples we have in, it's really the prototype example that we are working on. Typically, it's just an elliptic PDE where the uncertainty is in the coefficient. Basically, we have this x of m. We have the x just to avoid any type of additional box constraint in the inverse problem. So the right-hand side is a given source. We assume that that's known. This could be interpreted in the context of subsurface flow, for instance, in which case you could be interpreted as pressure, and M could be, for instance, log permeability. We will denote the parameter to observable map by this calligraphic F. And this involves the solution of the PDE given some parameter, followed by the application of an observation operator. So for instance, on the right, I'm showing some synthetic measurements. So on the top, I show a possible parameter field. And then on the bottom is a solution. The color shows the solution of this Poisson problem. And then we take that solution, we apply an observation operator to get this point-wise measurements and add some noise. Basically, this is how it goes. And the data or measurements, this is as I said, the solution U at some point. And then what else? So really the inverse problem is given measurements of the pressure at some locations, find the coefficient or the log permeability for this PDE. Okay, so this may be, again, very well known for some, but just in case you're new in this area. So typically one goes from given some inputs, solve the forward problem, and that's it. But for inversion, we are looking at some data, which is the output of the problem plus some noise. And here the noise is, I don't think I say it, but this can be modeled as a Gaussian with some mean and covariance. In this talk, I will consider that this noise subsumes pretty much noise coming from model error, from measurements, and so on. Now, while this forward mapping is, or better be, well posed, it has a unique solution, the inversion or the inverse problem is ill-posed, underdetermined. In a deterministic setting, one adds some regularization to deal with these issues. In a Bayesian context, this framework offers a way to describe the probability of all models that are consistent with the observations, and it allows us to incorporate any type of prior knowledge about the parameters without knowing anything about the data. And as I mentioned before, we used Bayes' theorem, which can be written as such when the likelihood is of this form. This is nothing but the misfit term between the prediction and the data weighted by the noise covariance. And so this term is the likelihood, and this is x of this guy is the prior. And as I said, we model the prior with a Gaussian with some mean that you somehow come up with, and the prior covariance, which will impose some sort of smoothness on your parameter. Okay, so what's the first thing you do? You approximate the posterior as you can, because despite this nice explicit form of the posterior, its exploration is difficult due to the high dimensional nature of the parameter and the potentially expensive PDE-based parameter to observer map. So in this case, perhaps it's simple, but I mentioned the ice sheet flow, which is governed by a nonlinear Stokes. So at every evaluation, you need to do some sort of Newton iteration to solve a nonlinear PDE, and so it can be very expensive. So to find the maximum a posteriori point requires solution of a PDE-constrained optimization problem. And basically, this is a deterministic inverse problem. And as I mentioned, we use inexact Newton CG, so we need to compute derivatives using adjoints, basically first and second derivative. And so this costs another 2 PD solves per gradient. And if you go to Hessian, then that's another 2 linearized solves. So it adds up. So to compute this map point, basically we just, in case you are not familiar, this is just taking the mean or argmean of the negative log posterior, which is the same as solving this optimization problem. Again, this is a kind of a deterministic type inverse problem with some special weights and special, if you wish, regularization. Now, when the parameter to observer map is linear, due to the particular choice of the prior and noise model, the posterior is Gaussian, and we know how to compute the mean. The mean will be the map point, and so, okay. And then the covariance is given by the inverse of the Hessian of this cost function. And here, this is the forward mapping, and this is the adjoint. So if you could, now, for instance, you can construct the Laplace approximation of the posterior, which is this Gaussian around the map point, and you can take samples from both prior and posterior, and this is, for instance, how it goes. This, for instance, you could look at the mean of the prior and then take some samples. Basically, this shows how much variation you have in your prior, and at the bottom figure I show the map point and then samples from this Laplace approximation. As you can see, the samples are quite less varying, which shows less uncertainty or less variation when compared to the map point, as it should be, because using the data, we basically reduce the variance of the prior quite a bit. In order to do sampling efficiently, we use low-rank approximation. And this is where I mentioned that in hIPPYlib we have implemented randomized SVD algorithms to compute the so-called important or more significant eigenvalues. And there is a little bit more to this story here. Basically, we look at the eigenvalues compared to 1, because we use the Sherman-Morrison-Woodbury formula, and that kind of tells us that anything less than 1 can be ignored, basically. Again, all these details are in the paper I posted as a reference. And the cost of low-rank approximation via this randomized SVD measured in the number of Hessian vector products. This is our currency. And one Hessian vector product, I want to emphasize that this costs about 2 PDE, linearized PDE solves. The nice thing is that it's independent of the data and parameter dimension. And so this really is a very good property to have when you want to solve large-scale problems. And these are just the eigenvectors showing high frequency oscillations as corresponding to low eigenvalues. Okay, so if things are linear, great, or if you are okay with the Laplace approximation, good. But in general, for nonlinear parameter to observable maps, the posterior is not Gaussian. In this case, one needs to use sampling to characterize the posterior. And so this gets us to some Metropolis, Hastings, Markov chain, Monte Carlo approaches to approximate some statistics. But sampling in high dimensions is challenging, as probably many of you know, because it requires many evaluations of the forward problem. We can, as I will show you, it's quite important to exploit low-rank properties of the Hessian if you use Hessian-based proposals and improve on the computational complexity of this method. Okay, so just a heads up, I will advocate for Hessian-informed MCMC methods, and I will show you, at least in our benchmark problems, we found that these methods are more effective. In hIPPYlib-MUQ, we use, this framework enables Hessian-informed MCMC that exploits the curvature given by the Hessian of the posterior. And we see significant improvement on the sampling performance, as you will see in the tables I will show you in a second. And we use low-rank approximation of the Hessian to do operations like square root apply or inverse square root apply or anything that you need to do in that. There are a couple of methods in MUQ that we look at. So these are some of the MCMC proposal distributions available in MUQ. And we started with the basics, but we were mostly interested in methods that give us some mesh independence. We also use proposals that use gradient information and Hessian-based methods. This is just a picture to show the relationship of these MCMC type approaches with respect to mesh refinement independence. At the end of the day, we want to push this for large-scale problems or larger-scale problems. Okay, just to define, this is random walk. We are looking at Metropolis adjusted Langevin, preconditioned Crank-Nicholson, some and the Hessian informed variants of PCN and MALA and all that. And this is one of the big ones we have spent quite a lot of time. We explored various posteriors. We explored posteriors using various MCMC methods, and we look at all kinds of convergence diagnostics and computational efficiency of the sampling approaches. We look at the acceptance rate, and we look at the multivariate potential scale reduction factor. Basically, this is closer to 1, the better the sampling, and the effective sample size. And we kind of count the number of PD solves in the process via this last column. That's basically our currency, because we want to track the number of PD solves that are needed to converge. Okay, under this metric, it seems that daily map is the most efficient method, and I just want to, okay, right, is the most efficient method. However, I would like to emphasize that there are more parameters to tune in this context. So we tend to like the Hessian informed preconditioned Cran-Nicholson because it's a bit easier to tune and gave us fairly good acceptance rate, MPSRF, fairly low number of PD solves, and not the greatest, but a good effective sample size. We used 20 independent MCMC chains, each with 25,000 samples, so a total of 500,000 samples for this particular run. We looked at also the autocorrelation function estimate of a quantity of interest. In this case, we looked at the log effective permeability, and we looked at this for several MCMC methods. And as you can see, most of the Hessian-based, Hessian-informed methods do quite well in terms of efficiency or convergence. Yeah, basically same results shown in a different way. If you want to look at some trace plots of the quantity of interest, this is how it looks. Again, PCN and all these things without Hessian information, it's really terrible, if I may. DILI map, which is the dimension independent likelihood informed MCMC method, using the Laplace approximation, I think, at the map, did quite well, as I mentioned. Okay, we pushed the problem a bit to higher dimension, and we went up to about 66,000 in terms of parameter. The nice thing is that for HPCN, as I said, we kind of liked it because the good performance, but also easy to tune. The acceptance rate, what was nice, this is showing actually mesh independence. The acceptance rate stays about constant, about same MPSRF, and the effective sample size is quite stable. And also the nice thing is that if you look at the Hessian at now, I think this is a fixed Hessian for different mesh sizes. It shows that the spectrum is also doesn't change with when you increase the number of parameters. Okay, as a summary, I presented the robust and scalable software framework for the solution of large-scale Bayesian inverse problems governed by PDEs. This framework integrates 2 complementary open-source software libraries, hIPPYlib-MUQ. The objectives are to provide domain scientists a suite of sophisticated and computationally efficient MCMC methods that exploit Bayesian inverse problem structure and allows you to perhaps more easily implement new methods and compare against state-of-the-art. I would like to bring your attention to some of the limitations. We rely on Phoenix for the finite element approximation of PDEs. Therefore, we inherit all the limitations in terms of what you can solve with this, for instance, time-dependent problems, you need to do a bit more. And so all the limitations that are inherited from Phoenix, we have them in hIPPYlib. However, the Phoenix hIPPYlib-MUQ developers and user communities, I think, offer a rich support base that the users of this framework can build on. We are interested to extend support to alternative finite element implementations, and I think Umberto at UT is looking into Firedrake, potentially extend support towards that as well. And there is a lack of parallel implementations of MCMC methods currently in hIPPYlib-MUQ, and we hope that in future versions of hIPPYlib-MUQ to incorporate some multi-level parallelism. Excuse me. Okay. And another thing I want to bring to your attention is that despite the fast and dimension-independent convergence of these advanced structure exploiting methods that I mentioned, still many inverse problems governed by expensive to solve PDEs remain out of reach. So in such cases, there are so many other algorithmic developments and other methods to be exploited or implemented, tried. For instance, one could use various reduced models, surrogates, ideas to speed up the sampling process. One can also approximate Hessian to speed up any type of Hessian or sampling or Hessian action in the process. So a lot to be done, lot to be explored. If you have comments or if you want to contribute, please reach out to us, and we'll be happy to talk to you. And with that, I will stop here and I will take questions. Hi. No, we did not. We wanted to look at Hamiltonian Monte Carlo and also some of these transport maps, which are available in MUQ, but we couldn't really push those to solve the problems that we were working on. And so I think Matt was interested. Maybe you guys have even talked about that, but happy to try it down the road, absolutely. But we have not yet. Yeah, absolutely. Yeah. Okay, yeah. Oh, absolutely. And that's you know, at this point. So my postdoc, Kite, had to finish, and we had to kind of close the loop on this project. But absolutely, that's on our radar. Absolutely. And we'll reach out down the road. Thanks. Yeah. When you say a base solution, or did you mention Stokes? Okay. I think we are not doing that great on that side. I think the users are mostly collaborators at this point, and students who came to our workshops and summer schools, and we track our user community. We could do better, but I think it's still difficult without some help from our end. It's still difficult for someone to just start running things, even though we offered all the implementations and examples via this Docker image. it's still difficult, I think, for a user who is not in constant touch with us to start working and using this framework. So I'm hoping to do better. And one of the reasons I give these talks is to attract interested folks to try it out and ask questions and reach out to us, and that's how it goes. If you have any other recommendation, let me know. Absolutely. Yeah. Yeah, that's exactly, that's right. So definitely we need to do better in just reaching out to more interested researchers and students. And also I would like to mention that the funding has ended, which puts a little bit of difficulty, but we applied for something new and we hope to get more funding in the fall. And in that case, we'll be looking for a postdoc in that case. So if you are interested or anyone is interested to work on these things, reach out down the road if possible. He's not applying, right? I know. Yeah, yeah, yeah. Hmm. Yeah. Oh, can I just say that we are in touch with Linus, and there were meetings and there were some benchmark problems. Hmm. Yeah. Yes, yes, yes. Hmm. I absolutely. I agree. First.